Okay, continuing with integrals that involve exponential and log functions, let's do a couple more examples. This one might actually look difficult, but it's really not that difficult if you make the right substitution. If you actually let the denominator be u, you'll find that the numerator is actually du, this portion right here. Because if u is e to the x plus e to the minus x, then du would be e to the x minus e to the minus x dx, which is the numerator. So actually this one can just be written as the integral du over u, where u is e to the x plus e to the minus x. And then that equals the natural log of the absolute value of u using your log formula plus a constant. And then at the end we replace u with what it equals here, e to the x plus e to the minus x. Now on this one, you can use a u substitution as well. You can let u equal the natural log of x, and then du equals 1 over x dx. So actually you might want to rewrite this to see it written this way. It's the same integral, but this way you can see that now you have e to the u, and then 1 over x dx is du. So this is the integral of e to the u, and when you integrate e to the u du, you just get what? E to the u plus a constant, which would be e to the natural log of x plus a constant. Well, guess what e to the natural log of x is using your log properties? E to the natural log of x, since natural log has base e, then e to the natural log of x is just x. So that's x plus a constant. Well, I kind of tricked you here because I was just kind of messing with you on this one. Actually, you could have done this a lot easier if you had said in the beginning that e to the natural log of x is just x. Because if e to the natural log of x is just x, then this is just x on top and x on bottom. So this is just the integral of 1 dx. And when you integrate 1, you just get x, of course, plus a constant. So anyway, that's sorry about that. I didn't mean to be mean to you. Okay, now let's take a look at an application. This says the market research department for a department store has determined that for one particular store, the marginal price, P prime, at X tubes per week of a brand of toothpaste is given by this formula. So this is P prime. Now, what it wants us to do is to find the price, or the demand equation, P of X. Well, if we know what P prime is, and now that we know how to integrate, we can get P. So basically, let's see what we can do to get P. Well, P would have to be the antiderivative of P prime. So P would be the antiderivative of, and here's P prime inside this integral. So it would be P would equal minus the integral of minus 0.015 e to the negative 0.01x dx. Now actually I could use my little trick here that I showed you. So I have negative 0.015, I pulled it on the outside. Now for this inside I could use that little trick. Remember earlier I showed you this little trick you could use. Where is it? Right here. E to the ax is actually, and when you integrate it you get 1 over a e to the ax. So you could use that little trick there, but I went ahead and did substitution. I didn't. I did use the trick. Okay, so when you integrate this, it's actually 1 over negative 0.01 times e to the negative 0.01x, and then you're going to multiply that by negative 0.015. Well, long story short, if you take negative 0.015 and divide it by negative 0.01, you're actually going to get 1.5. So you're going to get 1.5 e to the negative 0.01x plus a constant. So the question is, how can we get that constant? Okay, well, if you go back and read the problem, you'll see that when x is 50, the price is given to be $2.35. So that means if I evaluate this p function at 50, the answer should be 235. So let's put 50 in here for x and set it equal to 235. So if I put 50 in here, that'll give me 1.5 e to the negative 0.01 times 50 plus c equals 235. Well, then if you solve this for C, you'll get C is 2.35 minus this expression 1.5 e to the negative 0.01 times 50. Well, I just plugged this into the calculator and calculated it, and I got 1.44 for C. So now that I know C, I can go back to this function and replace C with 1.44. So now, remember I told you before you couldn't get the constant unless you had additional information. And since I had additional information, I knew when X was 50 that the price was $2.35, and that allowed me to solve for this constant. So now the second part of the question says find the weekly demand when the price is $1.89. So in other words, what's X when the price is $1.89? So this is just an algebra problem. Replace the price with $1.89 and then solve this equation for X. Well, we can subtract $1.44 from both sides and get 0.45 equals 1.5 e to the negative 0.01x. Well, if you take 0.45 and divide it by 1.5, you get 0.3. So we get 0.3 e to the negative 0.01x. And then you can just take logs of both sides. The natural log of 0.3 equals the natural log of this exponential expression. And you know the natural log of e to a power is just the power, so that's just going to be negative 0.01x. And then to finally solve it, take the natural log of 0.3 divided by negative 0.01, and you'll get that X should be 120 tubes of toothpaste. Now, I just think this is a cool application. So in finite math, we find the area under the curve of the normal probability distribution. Now, these areas actually give us the probability that an event will fall within a specific range, like what is the probability that a microprocessor will last between 10,000 and 15,000 hours, or what is the probability that a fish in a lake will be longer than 8 inches, and things like that. So in finite math, we have to standardize the value by finding corresponding z-values. Then we look up these z-values in a table, and guess what? This table gives the area between the mean and the z-value. I tell students that these areas actually come from calculus applications. So let me just show you this. The standard normal probability density function, which you don't have to know this, but I'm just going to show you because it's kind of complicated. The density function is actually like this. So if you wanted to graph a normal curve, if you had the mean and the standard deviation, you could actually graph it, because the formula is 1 over the square root of 2 times the standard deviation squared pi times e to this power, where this power is e to the, I believe that's a minus, e to the minus x minus mu quantity squared over 2 sigma squared. Let me double check and make sure that's a minus before I tell you wrong. Yes, that is a minus right there. So it doesn't show up very well with the division sign. But anyway, just keep that in mind. Okay, so if your data was normally distributed and you had a mean of 200 hours and a standard deviation of 10 hours, then you could actually plug 10 in for the standard deviation everywhere you see the sigma, and then plug 200 in for the mean, which only occurs right here. And simplifying that, I get this ugly looking function. Now if you graph that ugly looking function, it's going to look like this. And what's interesting is if you integrated this, and we're going to talk about area later, but actually integrals will give us the area under a curve, and the way you integrate it, and this is a definite integral, so I haven't talked about this yet, but let me just show you. If you integrate this integral from x equal 200 to x equal 220, then basically what it would do is it would give you the area under the normal curve from x equal 200 to x equal 220, and so that area, when you integrate this, turns out to be 0.475. And if you actually look up the z-values if you look up the z-value that corresponds to z equal 2, you should get a number very close to 0.475 in the table. And so basically those values in the table, those areas they got under this normal curve in a z table, is actually from using calculus, and someone went through and programmed it where it would calculate all of those areas for you using a computer program, and that's how it was generated. It was basically generated from this function. Now, something that's interesting is if you took this function, which would be the standard deviation, would be the formula for if the standard deviation was 0 and the mean, if the mean was 0 and the standard deviation was 1, you would get this function. Again, that's a negative. Okay, now what's interesting, you may find it interesting, I don't know, but if you find the derivative of this, and I'll leave you to show that the derivative of this is actually x squared minus 1 times this expression. Well, if you set this equal to 0 to find critical numbers, you would find that the critical numbers would occur when x is either 1 or negative 1, and this is the second derivative, okay? So I didn't mean to say critical numbers, I meant to say points of inflection. So if you found the second derivative, you would get this, and then this is equal to 0 when x is equal to plus or minus 1, and you could actually test the intervals and show that when x is negative 1 and x is plus 1, you get points of inflection. So it would actually change from curvature from concave up to concave down, then back to concave up at x equal negative 1 and x equal plus 1. Now this graph is not labeled the same as for this, but basically it looks the same. You would just have 0 here, and then the standard deviation would be 1. So one standard deviation would be this at minus 1, and another standard deviation to the right would be at plus 1. But anyway, I just thought you might find that interesting. It's not something to lose a lot of sleep over, but sometimes I like to throw some interesting stuff at you, even though you probably will never see it in the classroom. At least in the business calculus classroom. You might see it in another classroom.